Today we're going to study Snell's law. Let's see, for example, we have some, this is some water level, like in a swimming pool. So here we have water, and here we have air. And let's see some beam of light comes from the sun and hits the surface of the water. So here is the beam of light. And here is the vertical line. This vertical line is perpendicular to the surface. So this beam of light hit the surface at this angle. I call it here, for example, theta top, because this angle is at the top. Now, this beam of light, it was in the air coming in with approximately the speed of light, c. So we assume air as vacuum. It's not actually vacuum because you have a gas, you have oxygen, nitrogen, so that you have a medium. So the light is not really coming with the speed of light. It's coming with some velocity less than the speed of light. But when this beam enters the water density is higher than air. The air density is about like 1.26 kilogram per meter cube. But the water density of fresh or clean water density is about 1,000 kilogram per meter cube. So the light will slow down, will not go with the speed of light, will go with some speed, we call it v. So here at the top we have the speed of light, and here we have the velocity v. So the light will refract, will go something like that. And with some angle, I call it theta bottom. So this angle here, this angle is theta bottom. Theta top, theta bottom. Now, you can see that this angle here, theta bottom, is less than theta top, because you can see here the velocity, because we're in two-dimensional surface, it has two components. Now, you can see that this component here, coming in the y direction, the velocity is less, so it's going to shorten. It's going to shorten, so the beam is going to refract. So, like I said, the reason this beam refracts is because the water is a medium that's going to slow the light. So here at the air, we have an index, and the index, I call it n, so I call this one n top. And here, I call it n bottom. So n top is equal to the speed of light in a vacuum over the speed of light in air. Okay? Now we assume that the speed of light in air is closer or equal to the speed of light in a vacuum. So here we just have 1. So the index of air is considered to be 1. You can see here there is no units. The unit cancels out. This is meter per second cancel out, so you just have 1. If you come here to NB, this is the index of the water. The index of the water is the speed of light in the vacuum over the velocity of light in the water. This velocity of light in water is small compared to c. So actually this one is bigger than 1, because this velocity v of light in water is less than the speed of light c. Now, with Snell's law says that the index, I put here, n top, the index of this medium here, times sine the angle here, I call it theta top, is equal to index here at the bottom, n b, sine theta b. So this is a Snell's law. Okay. Now, since n top is 1, this becomes sine theta top is equal to nb sine theta b. So if we change this formula, we can write sine theta b is equal to sine theta t, or top, over nb. So you can see that this sine is less than that sine. Now if we draw the triangle, the trigonometrical circle, okay, so here is an angle theta, for example. Here is its sine. So if the angle is bigger, the sine, look at here, this sine here. Look at the sine of this small angle here. So if theta is small, its sine is going to be small. So if theta is like theta, this theta here is bigger than the other theta. So the sine is bigger. The sine, you can see here, the sine of this is bigger than the sine of that. So here, this formula, if I come back here, I can say that theta b is less than theta t. Okay? Now, let's see, for example, we are in swimming pool. Okay? Here is the swimming pool. Okay? This is the swimming pool. And then here we have air, and here we have water. So this is the water. Okay? Now, we're going to apply Snell's law to this system. Let's see. Remember here in this example, the light was coming from the top, from the sun. Here is the sun here. The light is coming from it and hitting the surface of water. Here we have a flashlight. We're inside the water like that. And the light is actually coming from the water. Here is the beam of light. It's coming from this flashlight. And then hitting the surface. It's going to hit the surface here. Now, when it hits the surface, you can see here we have, this is theta bottom, because it's at the bottom. And look at here. This medium here has less density than that one. So the speed of light in air is going to be bigger than the speed of light in the water. So we have a refraction, but the angle will be bigger. So we go something like that. So this is theta top. So now what's going to happen, I can put here again NB sine theta B, I'm coming from the bottom, is equal to N top sine theta top. This is, by the way, Snell's law. this law here. It's called Snell's law. Now, we know that theta top, or we know that this medium is just air, so its index is just 1, so we put here 1. So the formula changes, becomes NB sine theta B is equal to sine theta top. Now what's going to happen, something interesting is going to happen. If we increase this angle, let's see if I shoot the radiation at some angle bigger like that. This refracted beam will go this way. If I come closer here to the surface, the refracted will go this way. But then, at certain angle here, some critical angle, let me draw it in this color. This is some critical angle, theta critical. And this, at this angle here, the beam actually will refract. Will reflect. So if you keep increasing the angle, and the beam is coming from the water here in the air here, at certain critical angle, you have a total reflection. Now, once you pass, because what I did here, I passed a little bit the critical angle, I passed it a little bit, and then I got total reflection. But at certain location, you're gonna get the beam going like that. Right before it reflects, right there, the beam will go like that. So if we apply the formula, let me see, I apply the formula here. I can say, I put here NB, and I put here sine theta. This is when I don't pass this critical, right when the refracted beam go like that. So I put here theta critical, okay, is equal. I have 1 from the index because this is air, has the index 1. And then this angle is 90 degrees. So I put here sine 90. Because you see this angle here, because the beam got refracted like that with the horizontal. So it's 90 degrees from the vertical. So that angle is 90 here. But what is sine 90 is 1. So look what happened here. Sine theta critical is equal to 1 over NB. So if you pass this theta critical here, if you pass it, you're going to get total reflection. So any beam that's going to come bigger, any beam that's coming at an angle bigger than this theta critical will just have a reflection. You don't have a refraction. Just reflection. And if you go below this theta critical, you will have a refraction, and also remember the light reflects when you have, for example, some surface. This is like a piece of glass, and then you send a beam of light like this. This is glass. Some light will reflect and some light will go through. Okay, so if you have some medium like glass or water or some transparent material, the light, some of it will reflect, some of it will go through. Okay, so this Snell's law, it tells us that theta critical of this medium for the water. So if you want to know the index, or you want to know the speed of light in a medium, because this NB, what is it? It's the speed of light in vacuum over the speed light in a medium. So if you want to know the speed of light in certain medium, you just shoot the light from that medium to go outside, and then at theta critical, when the light goes parallel with the surface, you stop there, get that angle, plug it into this equation, and you can find the speed of light in that medium. So this formula here, I can change it to this. I can put here sine theta critical is equal, I put here NB, I put the speed of light, and over V in that medium. This is the velocity in the medium. What is this? This is just V over C. So the velocity in the medium, you can find it, just would be C times sine theta. Okay?